This talk is about escaping from auto-manual testing. So can I just see a show of hands? Who's ever written a test? Good. Has anybody here written a test and then discovered a bug after they wrote the test? And you all feel that this is kind of unfair? Yeah, me too. So this is about a library that I work on, which is aiming to make your tests more powerful, discover more bugs with less work from you, the programmer. So let's get started. The idea is called property-based testing, and you'll understand why in a minute. I'm going to walk you through an example of a property-based test, from coming up with the property that we want to test right through to getting a correct implementation. So we start with a simple example. I'm not claiming that this is an example of a thing that you actually should test, but it's a good example to teach you what this testing style looks like. So we start with pretty standard unit testing. We have two tests, one that checks. So the property we're testing is that the sum of a list of numbers is greater than the maximum of the list of numbers, right? You add up your numbers, you expect a bigger number than you have in the list. And our initial test, we add up a list of small numbers and we check that that's true, and we add up a list of big numbers and we check that it's true, but we can do better. So the simple way is to parameterize. We go, here's all the inputs we want to test, and for each of those, we run the test. And if it fails, PyTest or our other test runner of choice will helpfully tell us which of our examples were no good. We can do better again. With hypothesis, we can say, instead of checking these specific lists of integers, please generate any possible list of integers. And in practice, this will try a few hundred examples. So if we run this test, we learn something. And specifically, we learn that you can't take the maximum of an empty list. Instead, you get a value error. So we think, okay, we didn't actually want to check that. So instead, we tell hypothesis, look, we want lists of integers, but lists have to have at least one element in them. And when we run that, we discover that, of course, the maximum of a list of one element is the same as the sum. So we go greater than or equal to. And if we run this one, we discover that if we have negative numbers in our list, then the sum might still be less than the maximum. So we tell it that we want integers at least 0 in a list with at least one element, and now the test passes. So this style of testing can be applied to a very wide range of things. I'll walk you through some of how you can generate data, how hypothesis works, and what to do with it for the rest of this talk. But the basic principle is that humans are not so good at thinking up thousands of slightly different tests. That's the kind of work that we should leave to computers, and because we're programmers, we have a program to do that. So hypothesis gives you a huge number of ways that you can describe your inputs. We've seen lists of integers, but there are a number of other strategies, we call them, to generate values or collections of values. Most of them, we have none, booleans, floats, integers, date times, all the kind of standard library types that you might use. Where it makes sense, they all have minimum value and maximum value arguments. So if you have a more constrained test case, you can support that quite easily. And collections always have min size, max size. Where it makes sense for a particular kind of thing, there will be additional keyword arguments. So if you're generating floating point numbers, as well as capping the values, you can also specify that you don't want infinity and you really, really don't want not a number. Nobody wants not a number. Strategies, of course, may not immediately give you what you want, so they also have map and filter methods. So if you want even numbers, you just take any integer, then you multiply it by 2. For filter, you get more or less the same thing. You take your strategy and you give a function and you only count values from that strategy if the filter returns true. So I've got demonstrations here. If we take an integer strategy, you map the string type over it till you get strings composed of digits. You can map a multiplication by 2 to get even numbers. You can filter by modulo 2 to get odd numbers. This is actually relatively inefficient because hypothesis will have to keep trying to generate numbers, and whenever it generates an even number, the map or the filter will tell it, no, try again. It's smart, so it does learn from that eventually, but it's more efficient to multiply by 2 and add 1. And finally, you can do fancy stuff, like you want a list with at least 2 elements, with at least 2 unique elements, even though you allow repeated elements. There are various fancier things. I'm not going to go into these at great length. If you want to know more, I invite you to come to the open space later. You can have a deferred strategy. And deferred in this case means that the strategy can refer to itself in a recursive kind of way. So in this case, we're giving it either integers or lists of integers, or lists of mixed lists of integers, and so on forever. This one's particularly cute because you can define any value that's valid JSON in about 2 lines of Python. You can also draw data within your test, which becomes really powerful if you have a multi-step logic chain. You can, for example, do something, get your corresponding value, and then sample from parts of that, for example. And the composite decorator lets you define your own strategies in a completely from scratch custom way. The final thing which I find really useful when I'm working out what values to test is that often the kinds of values which your code accepts can be inferred from the code itself. If you've ever had a database schema, that tells you what valid things are for that database code. If you have a Django model, same thing. If you have a regular expression, we can infer what strings match that regular expression. If you have NumPy or Pandas data types, or classes defined with attrs, or a number of other things, even functions with type hints on them, Hypothesis can inspect this and work out what ought to be valid. In every case, you can also override that with explicit arguments, but if we can work it out, it'll do it automatically for you. So I'll talk briefly about cool stuff if you want to run this in prod test, testing stuff at scale. There are config options. Of course, there are config options. You can configure the verbosity, whether you have debug info. You can turn it into deterministic mode. We generally recommend leaving Hypothesis to do random exploration because it caches any bugs it finds. So if you run these random tests and you run them again and it found a bug the first time, it will never lose that bug. The internals are complicated somewhat by this determination not to lose bugs, not to be flaky, but we think it's worth it. There are more. You can define these in code, you can load them in profiles, you can get them from environment variables and so on. It's all in the documentation. Performance. Performance is a constant issue for these kinds of tests. And I'll say Hypothesis is fast. There's a statistics option. You can check how long it took to run your tests, to generate data for your tests, compare those, see the hotspots. And typically, somewhere between 0 and 20% of the time will be spent generating data to feed into the test. However, Hypothesis will run your test at least 100 times. If your test is slow, running it 100 times will not be faster. If your test is fast, running it under branch coverage, which Hypothesis does so it can tell when it's exploring new parts of the space, can also be slow. If it's pathologically slow, you can disable the coverage tracking, but it adds enough power that we recommend leaving it on in almost all cases. And the final thing I'm going to talk about Hypothesis itself is how it shrinks values. Because you might remember at the start, if we go back a bit, each time it gives us an error, it tells us the minimal falsifying example. So here, the list is just of the single element 0, even though this would also be true for a list with any number of zeros in it. Further on, the minimal list with a negative number is 0 and -1. This is kind of complicated how it works, but I'm going to walk you through the fundamental idea of it, because this really helps in defining your own data to make sure you get good behavior. It's essentially a 3-layer thing. You have the strategy function itself, or the strategy object, which you've composed out of all the parts Hypothesis provides. This basically translates up and down from a stream of bytes. When you're generating data initially, these streams of bytes are just random, or pseudo-random guided by coverage, fuzzer sort of thing. Here represented as just a stream of bits, because bits are easier to read on a slide than bytes. And then those are translated by the strategy into the actual values that we want. So in this case, we're asking for lists of at least 3 Boolean values. We have this infinite byte stream, and we have our output. Let's see what the minimal example Hypothesis finds is with the constraint that some value has to be true. That is, the predicate is the any function. The first thing that Hypothesis does is just observes that, well, the stream's not infinite, right? Because the minimal value must have fewer bytes of entropy to draw from. So we can just chop it off, and if we ever try to generate something that needs more, we just throw it away as a bad example. The next thing we do is we try to just set a byte to 0, or a smaller number. But for bits, you've got 1 or 0, so it's just set to 0. And we do this, and the predicate still passes. So we keep going. We try setting the next bit to 0. And the way this works, right, is that for ones that we know we have to have, we just treat each of those bits, or bytes, or collections of bytes in the real shrinker as values directly. But once we get to things beyond the constraint, first we draw a bit to say, do we want another value or not? And then we draw the bit for the value. So if we drop that to 0, our list is now of length 3. And hypothesis goes, I wonder if I can chop off those last bits. And it can. So now we only have 3 bits of entropy. And the problem here is it tries to flip that last one to 0, and now the predicate fails. In a real test, it runs the test with this new input, and the test no longer fails with the same error. So instead, it tries to perturb that byte stream bit. It just adds 1 to it and tries to shrink again. And in this case, it can shrink further once it's done that. And this is the minimal list, the smallest possible list according to the heuristic we use, which still passes the predicate any. I have time now for some questions, if anybody has questions about what you do with this or what it's good for.
It looks pretty cool. Hypothesis looks great, thank you very much. Two kind of related questions. First of all, do you have examples of, say, like user inputs that you can use, or like SQL injection strings that you could pass to your I don't know, your view and say, try all these things that are known to like break lots of views? And secondly, in your examples, you were basically looking for an exception. But what happens when you want to check what the like? You obviously don't know what the answer should be because the input's random. So do you write certain tests where you're like, as long as it doesn't throw an exception, I don't really care what the answer is for my function? Or how in the real world do you let's say we have a function which tries to find the first day in a month, and you give it lots of different dates, and it finds where the first day is. You don't know what the answer should be depending on what the date is. How do you deal with that, or do you just look for no exception?
So the first thing first, we have heuristics for things like floating point numbers or Unicode strings, which will throw nastier inputs at you more frequently than they would generally come up. But if you wanted to do something like testing injection strings specifically, I would do that with something like the sampling strategy, where you hand it a sequence of inputs and it will just give you one of those inputs. You could say, test any string or a string sampled from this list of known problems. For the second part, the bit of my talk which we'll go to next is on how you find properties to test which may expose bugs even when you don't know the exact answer. Anyone else?
I think you hit at this, that when you have a test that fails, hypothesis somehow is able to remember this or record this.
Yeah.
And I wonder how that's implemented and how's that exposed, because one of the reasons I write a test is, I've hit a corner case that I don't know. I will write a test to actually document the fact that I've had to handle this corner case because it wasn't obvious, et cetera, et cetera. So how does hypothesis expose these corner cases that have failed to the programmer? Are they documented anywhere?
Yeah, so there are two parts. The first is the way we cache it is by storing that underlying byte string. So we just have a file structure that we dump in a directory, which is in the standard Python gitignore on GitHub now. And if you rerun a test which has previously failed, it will first run all those failing examples to check whether or not they've been fixed. If you want to document a particular edge case or bug that you know is failing, sometimes we would just say, why not write a standard unit test for that? Hypothesis is great, but I'm not saying it's the only thing you should use. We also have an @example decorator. So you say @given list of integers, then you can say @example some specific list of integers. And it will always try that one before it starts the random generation.
In the example you gave, we're dealing with inputs of the form of strings or integers and so on. What if the things that you might be testing are relationships of a Django model in a database, for example, that are not that kind? They're a different kind of thing altogether. How would you find out whether certain relationships are likely to produce anomalous results from your code?
Partly if you can write an assert for it in Python code, which can be reached by feeding it pseudo-random inputs, hypothesis stands a decent chance of finding that. for specifically more complex data types, there are a number of strategies to help with that. For example, the build strategy, you pass it a callable, and a strategy for each of the positional or keyword arguments to that callable, and it will draw from those arguments, pass it to your callable, and give you that object. For Django specifically, we have a Django plugin, which will generate your database model, save it to the database appropriately, and so on. Any others? I'll take one more and then move on to some tactics for using hypothesis.
Just a quick one. How would you recommend to do the test for multiple inputs provided by hypothesis without re-implementing the exact thing you're trying to test in the test itself? For example, if you're testing something that converts a dict to JSON, in the implementation you would call JSON, but you don't want to do that in the test. You just want to compare with the actual string.
Yep.
So how would you recommend something like that?
Perfect question to move on to the next part. So the second half of my talk is on how you find or choose properties that might reveal bugs in your code when you test them. So the classical one, which is fantastic if you have it, is called a test oracle, an implementation that you know gives you the right answer. So it's pretty simple. You test your version and you test their version with the same inputs, and then you compare them. If it's the same, your version is correct, defined as the same as the other version. Great for rewrites or refactorings. New hotness equals legacy. Great for fancy algorithms. If you have some linear time sorting algorithm, congratulations. And you can compare it to a brute force sort to check that it really is sorting. If you have a multi-threaded thing, you can test it against the single-threaded version of that. If you have a test oracle, use it. If you don't have a test oracle, there are still things you can do. One of them is function inverses. For example, serialize your data, deserialize your data. You should get the same data back. If you don't, you know that you've got a bug somewhere. Add and subtract does a similar thing. These don't have to be strict inverses in the mathematical sense. You can also, for example, set some attribute of your object, then get the corresponding attribute, and expect to get the thing that you set. Append something, find the index of it in a list. There's another class of problems where solving them is hard, but checking a solution is easy. Solving a maze, finding the prime factors of something, tokenizing an input language. It's relatively easy to reverse from your input and check that you got something back, or at least something reasonable. Last one, almost the last one. There's a lot of invariance in your code where you can say, doing this operation shouldn't affect anything. So you do the operation and see if it did. Sorting a list twice should give you the list that you got from the first time sorting it. When you sort a list, you should also have the same number of each element as when you sorted it. That's half the definition of sorting, the other half being that the elements are now ordered. And the final one is that there are idempotent or nullipotent operations where if you keep repeating them or if you do them, you know that you have invariance of your system that you can check each time. On that note, I'm going to stop giving examples and go back to some more specific questions for people.
So if you have this cache of known bad inputs that might cause problems, and you have, say, you have a bunch of developers, do you have them each with their own cache, or and CI with its own cache as well, or can you share this somehow?
So the cache is designed so that it does work correctly if you just check it into your Git repository. That said, we find it doesn't usually help that much, so we recommend persisting the cache between CI runs, persisting it on each local development machine, but not bothering to share it between them. Whether you do or not will depend largely on what your team is working on, but for the general case, we wouldn't bother doing that.
How would you get started adding hypothesis into a system that had always been designed around many slower artisanal handcrafted tests? Like where to crack the nut?
It really depends on what your tests are checking. But one that I've had great success with is just to find a function, in a core somewhere that you know is called a lot. Work out what you think are valid inputs and just call the function. Don't assert anything about it. Just see if you can call it with inputs that might come up and see if that can ever trigger an exception. Once you've done that for a few, dateutil has, I think, 2 tests with hypothesis, both of which are testing that various formats round trip successfully, that dumping something to an ISO formatted string and reading it back from that give you the same date time value. Look for round trips, look for test oracles. There's a number of things. I'll post my slides on the Slack channel in a few minutes, and there are links down the bottom of each slide to some more resources to follow up on, or come to the open space and ask me in more detail.
When exactly are you doing the open space?
In the talk slot after afternoon tea, I'll be upstairs, or just come find me anyway.
Any other questions?
If that's it for questions, I guess the final pitch, it's under the MPL, so it's open source. You can use it for anything. We love new contributors and will actually help you write patches. And if you're some corporate organization with more money than time, we also offer training or sponsored feature development if there's something it doesn't do. So thank you very much.
Thank you very much.